Hello everyone, my name is Dhanashree Lonkar. My project partner is Kartik Parate. We are implementing feature extraction algorithm on FPGA DE-1 board as a term project of EE278 coursework under the guidance of Professor Charles Chu. In image processing, feature extraction is a special form of dimensionality reduction. Large size images contain many redundant pixels, which do not contain any useful information. So such pixels need not be sent for processing. So in feature extraction, we extract only those points which contain useful information. These points are also called as feature points or corner points. Corner points are of interest because they contain maximum information as they have maximum change in intensity. Let us move to the feature extraction algorithm. Our input will be a gray level image of known size. Also, we will take expected known number of feature points as an input. In our project, we are using a Lena image of size 128 by 128 pixels as an input. Also, we have taken number of feature points as 3200. Now output will be a matrix of 3 by n size whose first row contains the degree of confidence for each feature in the list. Second and third row contains the x and y coordinates of the feature points respectively. Now in our project, we have first calculated image gradient of each pixel by computing convolution of input image with a predefined mask. We have taken 3 by 3 mask in our project. After finding image gradient, we have calculated covariance values A, B, C using the formulae as shown in the slide. After finding the feature points, they are sorted in the decreasing order based on degree of confidence. We have implemented this algorithm in MATLAB and C. We have also written hardware accelerator code in Verilog for our C code. Now let us go to the MATLAB. So this is our MATLAB code. So in our MATLAB code, we read the image through the function imread, and from that we have converted pixel values from the image, and these values are stored in the text file. Now I will read this text file in my C code. Let us go to the quarters. This part will be explained by Kartik.
So let us begin with the quarters code. Here we create a new project. We give the directory where we want to store the project. And the project, quarters, select the folder. Then we give name to our project, feature underscore extraction underscore quarters. Here we change that name to QSys. Next, next. Here we select the Cyclone 2 family, package FPGA, pin count 484, speed grade 7. You select the second one. Next, in simulation we select a model sim. Next, and finish. Now we open the QSys. Here we create a new component. We name it as our hardware accelerator. We give the name here as my component. Next, here we add our hardware accelerator file. We analyze the synthesis file. There are no errors or warnings. So next, next. Here in the different interfaces, we give the Avalon memory map slave. Next, on reset, we give associated clock. We remove the clock for S0 and we give the associated reset to the Avalon slave. Now we remove the interfaces with no signals, so there are no errors here, and finish. And we save this project. Now we add different components. Neos 2 processor. Select the economic board. On-chip memory. Select the size as 16 384. JTAG. Performance counter. And then our hardware accelerator code. We make the connections, give clock to the everything. Now we assign the base address. So now there are only two errors. These two errors are because we haven't connected Neostro with the memory. So we go in the Neostro processor and give the reset vector memory, the on-chip memory, and also the exception vector memory, the on-chip memory. Finish. So now there are no errors here. Now we generate the project, save the file, give it the same name as we used at the starting. Feature underscore extraction underscore QSys. So there are no errors and 48 warnings, but we'll ignore those warnings. Close this. Now in files, we add the files. We go to feature extraction, QSys, synthesis, and we add a .qip file here. Set it as a top level entity. Now open the assignment editor to give the pin assignment. Here we give clock. Location pin underscore L1. Then again another clock. IO and 3.3 V LVTTL. Save our project. And we compile our project. This usually takes a long time. So the project is successfully compiled with 24 warnings, but we'll ignore the warnings. Now we need to dump the code in our DE1 board. So we open the programmer. Here we add the file, go to the output file and select the .sop file. Here we have connected our DE1 board and we burn this file in our DE1 board. So the file is successfully burned. We save the file in the output files. Now we open the NEOS2 for Eclipse. We give the workspace a directory. Here we create a new NEOS2 application and BSP from template. We give the sopc.info file. We give the name as feature extraction. Select the hello world small because there is not much memory to run the bigger code on our D1 board. Next, finish. Here we open the hello world small code. This is the basic code for printing the hello world. So we build the project. Our project is successfully built. Now we run the project as NEOS2 hardware. We got the output on the NEOS2 console as hello from NEOS2. So now here we will write our own C code that we used for this project and burn that code. Save the file, build a project. Project is successfully built. Now we run the project. So our project is successfully built, verified OK. And we get this output on the NEOS2 console. And it takes like 5828 cycles and the features are extracted. And hence your project is complete. Thank you.